Hi everyone. In today's video I'm going to actually be doing an extension of one of my previous videos on non-orthogonal correctors, and this was suggested by one of you in the comments for one of my videos, and I'm going to be going back and looking at non-orthogonal correctors again, but this time actually looking in far much more detail on the method used to decompose the unit normal vector. Because this part of the process is actually quite confusing and isn't really very well explained in the literature. So I'm going to be diving in, showing you exactly how we perform the decomposition and actually what each of the different approaches mean. So by the end of this video, you're going to have a much stronger grasp of non-orthogonal correctors, and I know you're going to find it extremely useful. Okay, so let's start off with some background information first. So in CFD codes, we solve a variety of scalar transport equations, and the majority of these scalar transport equations contain a diffusion term. And if you're not sure what I mean by a diffusion term, I've got a few examples for you here on the slides. So if you look at equation 1, that's the momentum equation, and you can see that the diffusion term there is highlighted with the under brace. And we also see diffusion terms in the other equations. So for example, for K and epsilon in the K epsilon model, I've highlighted the diffusion terms for you there in equations 2 and 3. And for most of these, you can see that the diffusion term has a common form where it's nabla dot, or the gradient operator dot, product with some coefficient in the brackets, and then multiplied by the gradient of the quantity that's being solved in the scalar transport equation. So in equation 2 there, for turbulent kinetic energy, we've got nabla dot and then some diffusion coefficient there in the brackets multiplied by nabla k. So that's a diffusion term, and the majority of transport equations in CFD codes contain a diffusion term. And it's really the diffusion term that we're interested in when we're thinking about non-orthogonal correctors, and that's what we're going to be focusing on today. Now, because this diffusion term is so common and it appears in the majority of scalar transport equations, what I'm going to look at today for demonstrating the non-orthogonal corrector process is just to look at the simple heat diffusion equation, which you can see there in equation 4. And again, it's got the same form that the majority of diffusion terms have, but we're just going to ignore all of the other terms that may be present in the equation just to simplify things for this analysis. So we've got nabla dot and then K, the thermal conductivity, multiplied by the temperature gradient there inside the brackets. And that's a heat diffusion equation, or a Laplace's equation, if you're used to thinking of equations like that. So in the finite volume method, which is what the majority of CFD codes use to solve scalar transport equations, the general process that we go through for solving these equations is to start by integrating that differential equation over a control volume, or the volume of a cell. So if you think of your mesh is split up into lots and lots and lots of cells, and what we're going to do is just integrate that differential equation over one of the cells. And that's how we go from equation 5 to equation 6. We just integrate over the volume, so now we have a volume integral. And then the next stage in the process is to use the divergence theorem, or Gauss's theorem, to change that volume integral firstly into a surface integral and then into the summation over faces. And I'm not going to go through the detailed mathematics of that because I've been through that in several of my previous videos and also in my fundamentals courses, so feel free to look there. But the place that we get to is equation 7, where we have a summation over faces of that term in the square brackets. And you can see what we've got there. We've got the thermal conductivity, K, the area of the face, and then the dot product of the temperature gradient and the unit normal vector pointing out of the face. Now, just to give you some context and to help you think this through, where have these terms come from? Well, actually, if you look inside the brackets, that term is just a heat flux. So Q, if you think the heat flux, is going to be equal to Ka times the temperature gradient. And so really what equation 7 is telling us is that the summation of the heat flux out of each of the faces of our cell must be equal to 0. So really, this is just an expression of conservation of energy, is that if you take the heat flux through each of the faces of the cell and then add them up, the net heat flux must be 0, because we've got no sources of heat or sinks of heat inside the cell at the moment. So the net total of the heat coming in and coming out must be equal to 0 for this cell that we're looking at and for every other cell in the mesh. That's why we've got Kf, that's the thermal conductivity at the face center. We've got the area of the face, AF, and then we've got the dot product of the temperature gradient and the unit normal vector pointing out of the face. So again, the unit normal vectors always point out of the cell, so we're looking at the heat flux out of the cell. And just going back to what we said about before, here we're just looking at the heat diffusion equation, but this process of diffusion is going to be common and will appear in all of the scalar transport equations. So if you looked at the momentum equation or turbulent kinetic energy, for example, you'd also be getting a diffusion of quantities out of those cells as well. But we're just looking at the heat diffusion equation here because it's easier to follow and to actually think about what's happening as we go through the process, but it is identical for all equations. So now we're just going to have a little think a bit further about equation 8 that we're looking at, and why do we need the dot product in there? That's really the thing we're going to think about on this slide. We've got the dot product of the temperature gradient and the unit normal vector. Now, as we know from thermodynamics, heat flows in the direction of the temperature gradient, or more correctly, the negative of the temperature gradient. So heat will flow from regions of high temperature to low temperature in the direction of the gradient. Now, that is represented by the red arrow, which you can see there in the diagram. For whatever reason, the temperature gradient is going directly up in this example. And of course, the unit normal vector always points normal to the face out of the cell. So the key point here is to realize that the unit normal vector and the direction of the temperature gradient are not necessarily in the same direction. And that's the reason that we need the dot product in there, is because the heat will always flow in the direction of the temperature gradient, but we want the component of this heat that's flowing out of the cell normal to the face, which is why we take the dot product. And then of course we multiply by the area of the face and the thermal conductivity to give us the heat flux. So it's worth bearing that in mind as we go through the slides. That's why we have the dot product there between the temperature gradient and the unit normal vector. Now, when we construct and put together our CFD codes, the unknowns in the set of equations that we're solving are the flow variables at the cell centroids. So when we're solving the energy or temperature equation, really the unknowns in the whole system are going to be the temperatures at the centroids Tp and Tn there, which you can see in the diagram. And if you've been studying a lot of the CFD content I've been posting on this channel, you'll be well used to this by now. It's the temperatures at the cell centroids that we're interested in. But so far, looking at that equation that we've got there in the image, we can see we haven't got the temperatures at the cell centroids. We've only got the temperature gradient on the face of the cell. So somehow we need to express that temperature gradient in terms of the temperatures at the cell centroids. And this again will be true whatever scalar transport equation we're looking at. We want the values at the cell centroids. Because then what we do is we follow through the process and we rearrange the equations, and so we have our unknowns, which are the temperatures at the centroids of all of the cells in our mesh. And if you've looked through my fundamentals courses or my previous lectures, you'll be well used to that by now. So the first case we're going to think about is if that unit normal vector there, that's n with subscript f, the unit normal vector, if that's parallel with the vector between the cell centroids, so Tp and Tn, if we drew a line between those centroids, that vector would be dPn, to say that it's between centroid P and centroid N. If those two vectors are aligned, then it's actually very straightforward to actually work out this dot product. And I've got that for you there at the start of equation 9. You see the dot product of the temperature gradient and the unit normal vector, because they're parallel, is just going to be equal to the temperature gradient multiplied by the magnitude of the unit normal vector. So the temperature gradient in this case would be Tn minus Tp divided by the distance, because that's delta P over delta X. The change in temperature divided by the change in distance between those 2 points. And then we just multiply that by the magnitude of the unit normal vector. So if the line between cell centroids is parallel with the unit normal vector, NF, you can see there in the picture, then it's very straightforward for us to proceed. And we can substitute that expression there in equation 9 into our conservation of energy that you've got also there in equation 9, and just replace the dot product with the fraction which we see there. And that allows us to arrive at equation 10. And we can see what we've got is we've got the summation of Kf AF multiplied by Tn minus Tp over the distance between the cell centroids and multiplied by the unit normal vector will be equal to 0. And so what we're really doing is we would evaluate that on all the faces of our cell, and for each of these you can see that the unknowns in this equation are Tn and Tp, which are the temperatures at the centroids of the cell. And the way the CFD code would be assembled and works is you would write that equation for every single cell in the mesh, and then that would of course give you a coupled system of algebraic equations where the unknowns are the temperatures at the centroids, and then you would solve that with an iterative matrix solver. So very straightforward, and this is the standard process that we would follow for solving the CFD code when that vector between Tp and Tn is parallel with the unit normal vector, or more specifically if we have a perfect mesh. So if you've got a mesh of all squares or all rectangles, this approach is possible. And I do go through this approach, I think, in a lot more detail in my first and second fundamentals courses, where I go through all of the detail exactly, and you'll see it's quite straightforward to obtain a solution. However, this brings us to the topic of today's talk, which is the majority of meshes that you may have constructed and you may see in CFD codes are not made of perfect squares and rectangles. We often have triangles, tetrahedra. Often our rectangles and squares are skewed, so they're not exactly aligned, and that leads us to a situation which we can see there in the diagram on the slide, where if you look at that line between the centroids Tp and Tn, that's the vector dPn, that is not parallel with the unit normal vector. So the two vectors are not aligned, and it means that previous simplification that we used in the last slide we can't use directly to obtain a solution to the system of equations. So we have to do something a bit more clever. And unfortunately, because the majority of meshes aren't perfect squares and perfect rectangles, this actually turns out to be the normal case that we always have to do. We always have to account for dPn and NF not being parallel with each other. And what's the solution to this? Well, the solution, which I went through in the previous talk for non-orthogonal correctors, is to split that unit normal vector NF into two components. Now, I've called these components N1 and N2 here, and in the literature you may see these referred to as delta and K instead. I've chosen to use a slightly different notation here because I think it helps avoid confusion and helps us remember exactly what we're looking at here. I tend to find it's a lot clearer. So if you look at the diagram here, what we're doing is we've got NF, that's our unit normal vector, and we're decomposing it into two different vectors, N1 and N2. N1 is going to be a vector that's parallel with the vector dPn, and then N2 is just going to be the residual component, or whatever is left over after we've created that vector N1. And that's going to be the standard approach that we use to account for non-orthogonal and bad meshes. Now, some of you who've been paying attention so far and are well used to this non-orthogonal correction problem may have seen my previous talk, where it's not actually clear at this stage how we choose the vectors N1 and N2. And what I'm going to be showing you in this talk are the different methods that we can use to choose N1 and N2, and then the actual method that CFD codes use to decompose that unit normal vector NF into different components. So when we've made the decomposition, which I'm going to show you later, it's fairly straightforward to find a solution to the system of equations. If we start with equation 13, which we had before, and then substitute nf with n1 and n2, then we can split up that fraction, split up the summation into two separate summations, which you see there in equation 14. You've got n1 in the first summation and n2 in the second summation. Now, from that previous diagram, we saw that n1 was chosen specifically to be parallel with the vector dpn. And because it's parallel, we can use the approach that we used previously to simplify the first summation, and then we arrive at equation 15, which you can see there. You can see the first summation, we've now got Tn minus Tp divided by dPn in that summation. And because that treatment is exactly the same to what we've seen and used before, we can rearrange that term to set up our system of algebraic equations to solve using the CFD solver. However, the difference is now we've now got this second term, which we see there in equation 15, and this term is often called the non-orthogonal correction, or the explicit non-orthogonal correction. And the vector we've got in there, we've got n2 instead of nf, and that's the residual component from the vector decomposition. Now, at this stage, those two vectors, remember, aren't aligned. So the temperature gradient and that residual component of the vector decomposition are not parallel with each other. And because they're not parallel, it means we can't use that same fraction that we used for the first summation. We'd have to do something different. And the way we do that is by actually evaluating that dot product explicitly or directly using the temperature gradient that we computed in the previous iteration. And this is a fairly common trick that we use a lot in CFD, where if we don't know a component implicitly and we can't rearrange it in terms of the unknowns at the centroids, what we do is we take the values from the previous iteration, just evaluate them explicitly, and then add that on as a source term on the right hand side of our matrix equations. So that's really what we do here in equation 15. We treat the first summation implicitly, or we write it in terms of Tn and Tp, and then the second term we evaluate directly using the values from the previous iteration, and then add that on as a source term on the right hand side of our equations. And this is fairly common practice, and I did go through it in my previous talk on non-orthogonal correctors, so you should be used to this by now. And that just about wraps up the background for this talk. What we're going to move on to now is really look at the key point in this talk, which is how do we choose that vector decomposition of nf into the orthogonal and non-orthogonal components, or n1 and n2. How do we carry out that decomposition, and what's the best way of doing it? So to start things off, it's important to remember that actually there are an infinite number of ways we could perform this decomposition. It doesn't matter what we choose for n1 and n2, as long as n1 is parallel with the vector dpn. So just a reminder, if you look at the diagram there, you can see that nf is in red. That's the unit normal vector pointing directly out of the face, and then n1 is a vector that's going to be parallel with the line that goes between the two centroids across the face. And so actually there are an infinite number of choices we could make, as long as n1 is directly parallel and goes along that line. And I'm going to show you three different choices that are popular and have been proposed by the CFD community. The first method is to make a right angle triangle, and you may see this method referred to as the minimum correction approach, but I like to call it the right angle triangle method because it's a lot more descriptive and makes it exactly clear what we're trying to do in the decomposition. So if you look at the diagram there, what we're going to do is we're going to have n2 be vertical, or directly at 90 degrees with n1, and that's how we're going to perform the decomposition. Now, what I'm going to do for each of these correction approaches is to actually derive for you what the expressions are for n1 and n2, because often they're missing in a lot of sources, and I think it really helps us understand if we can actually go through the algebra as well to work out what these vector components are. So if we look at the diagram there, because we've got a right angle triangle, we can just say that the vector n1 is going to be nf multiplied by cosine of theta, where theta is that angle there. And in order to replace cosine theta, we can use the dot product identity, which I've put there for two general vectors, a dot b. And what I like to do, the way I derive these, is I like to get cosine theta and then replace that using the dot product identity. So if you do that, starting with equation 17, and then using the dot product identity to remove cosine theta, we arrive at the expression you can see there in the box in equation 18. So n1 is going to be equal to the unit normal vector nf multiplied by that term in the brackets. And this will give us an equation for n1. So if you think about what will typically happen in a CFD code, you create your mesh and then you pass the mesh from your mesh generator into the CFD code. And what the CFD code will do is look at all of the unit normal vectors and decompose those into n1 and n2. And this is an expression for n1, which the CFD code will calculate because it knows what dpn is, it knows where the centroids are, and it also knows what the unit normal vector is, nf. So you can just use that expression in the box and that will get you n1. It's worth also noting that n2 will then just be given by the second expression, which you can see there in equation 18. n2 will just be the vector subtraction of n1 from nf, and that will give us n2. And if you want, you can always try these out, by yourself. If you get a pen and paper and write down some example vectors, perhaps for nf and dpn, and try the formulas out, and you'll find that n1 and n2 will be at right angles to each other. And at this point, before moving on, I'm going to make a small point about why this approach is sometimes called the minimum correction approach, if you look at this in the literature. And the reason this is called the minimum correction approach is because it minimizes the size or the magnitude of n2. That's what this approach is attempting to do, is it wants to make n2 as small as possible. So it's called the minimum correction approach. And I'll go into more details later about why that is and what it actually means for the CFD code. But for us at the moment, what I think we need to do is think about what happens as the angle of that face changes. And I've got this for you in the diagram there, which you can see on the page. The diagram on the left shows what happens if the angle of our face to dpn is fairly small. If we've got a good mesh and theta is small, we can see that n2 is whatever size it is, and n1 is there as well. But now when we skew the mesh, or that face increases its angle theta to the vector dpn, what you can see is that n2 is going to grow there, and n2 is going to get a lot larger, while n1 is going to be getting smaller because of the right angle restriction that we've placed on that. And what does this mean in terms of the equations? Well, if we look back at equation 19, we can see that our first summation there has n1 in it, the magnitude of n1, and our second summation has n2 in there. So what's happening is that as the angle of that face is increasing, as theta is increasing and the mesh is getting more skewed, we can see that the magnitude of n1 is reducing and n2 is getting larger. So what this means is that the first summation, that entire summation term, is going to be getting smaller, and the second summation is going to be getting larger. And if we remember back a few slides ago, that first summation is treated implicitly, and these are the unknowns in our system of equations, Tn and Tp. And then that term on the right hand side, the second summation, is treated as a source term. So what's physically happening here is that as the triangle gets steeper, moving from A to B, the implicit term there is going to be getting smaller and the source term is going to be getting larger. So this means in terms of the stability of our equations, these equations themselves are going to get less stable and more likely to diverge as that angle theta increases. This is part of the reason why bad meshes lead to divergence in CFD codes, is because of the balance of these two summations. The source term getting larger, while the implicit or the first term is getting smaller. So now we've looked at the right angle triangle approach, let's look at a few others. The second method we're going to look at, I like to call the rotation approach, because it describes exactly what we're doing with the unit normal vector. In the literature, you may see this method referred to as the orthogonal correction approach instead. And what we're going to do with this approach is just take the vector nf and rotate that so that it's parallel with the vector dpn, but keeping the same magnitude. And so our expression for n1 would just be the magnitude of nf multiplied by the unit normal vector in the direction of dpn. And that gives us equation 20, which is an expression for n1. Now, this rotation approach is slightly different to the right angle triangle approach that we saw before, because as we increase the skewness in the mesh, or increase theta, we see that the magnitude of n1 stays the same, or the size of that first term in our summation, that first summation is going to stay the same as the mesh skews and gets worse. Now, that's not the only approach we can use. There is another approach which I'm also going to present and discuss with you quickly here. Now, the third approach is called the over-relaxed approach. You'll see this one referred to a bit in the literature. And it took me a little while to work this one out, but actually with the over-relaxed approach, you can see that the trick is to make n2, so that residual vector, the green vector, perpendicular to the vector nf. So the right angle is sitting at the top of the triangle there, instead of at the bottom, which is what it was before. And with this over-relaxed approach, again, we can do some quick trigonometry to work out what n1 is, and then n2. Now, if you find this one in the literature, you'll often find that the derivation for n1 is missing, so it can make it a bit confusing to see how they've arrived at the expression they have. But I'm going to actually give you the full derivation here, because I managed to work it out. So if we start by just thinking of that triangle and looking at the angle theta, then cos theta will be the magnitude of nf divided by the magnitude of n1, and we can rearrange that in equation 22 to get the magnitude of n1. And as before, I like to use the same trick using the dot product definition to eliminate cos theta, and that allows us to arrive at equation 24. And this, of course, is the magnitude of n1 is equal to the magnitude of nf multiplied by that fraction there. And of course, this is a scalar, which gives us the magnitude of n1. We now want the vector, which is going to be the magnitude of n1 multiplied by the unit normal vector in the direction of dpn. And so we do that. If we take the magnitude of n1 and multiply that by the unit normal vector in the direction of dpn, that gives us equation 25. And then we can simplify and cancel out terms, and that allows us to arrive at equation 26. And you may find that expression in the literature, but this gives the complete derivation now, so you can see where it's coming from. And of course, once we have n1, as before, we can get n2 by subtracting nf and n1, and that will give us n2. So we get both components of the vector. Now, with the over-relaxed approach, we want to have a little think again, what happens when the face gets more skewed, or when theta increases. And what you can see from the diagram there is actually as theta increases, n1 is going to increase this time, and n2 is also going to increase in magnitude. And if you look at equation 28, you can actually see that the dot product there is on the bottom. So as the angle increases, the dot product on the bottom is going to reduce and get smaller. And so because the bottom of the fraction gets smaller, that means that n1 is actually going to increase. And so that pink vector, which you can see there, is going to increase in size. So I presented 3 different treatments for you here of how we can decompose that vector nf into different components n1 and n2. And in all cases, n1 is parallel with the vector dpn, and so we can use the same orthogonal correction approach for all 3. However, which of these decomposition approaches is the optimum, which is the best, and which is the one that's actually used by CFD codes? Because this approach will often be hard-coded into CFD codes and can be quite difficult for you to find out actually which version does the CFD code use. And a very useful comparison of these methods was given by Professor Jasak in his Thesis from Imperial College London in 1996. And that thesis is available online, so if you actually want to go in and have a read, I'll put a link in the description below for where you can find his thesis. It's really, really good. And these particular results that I'm going to present to you, I've also page numbered as well, so you can actually jump exactly to the figure if you want to see where these have come from. And what Professor Jasak does in his thesis is takes a comparison of the three approaches on meshes with different degrees of skewness in them. And this first set of results I'm showing you here is for a uniform face angle of 30 degrees. So all of the faces in the mesh are skewed by 30 degrees. And in the plot there, what you can see is the number of non-orthogonal corrector loops along the bottom of the axis, and then the accuracy of the result scaled on the vertical axis there. And what you're seeing there is that we have to take several consecutive non-orthogonal corrector loops to get a converged solution. What does that actually mean? Well, because that explicit source term, we take the values from the previous iteration, that means that that term is lagged behind the implicit term. And so we actually have to iterate several times until those terms actually converge. And that's true even for a simple Laplace equation or heat diffusion equation. We have to continue to loop through each time updating the source term with the temperature gradient from the previous iteration in order to get a solution. And what you can see in this graph is that up to 30 corrector loops or 30 iterations of the solver were carried out. And what you'll see is that actually all three approaches, the right angle approach, the rotation approach, and the over-relaxed approach, give the same solution. So when we've taken enough non-orthogonal corrector loops, we will arrive at the same solution. And that's because the temperature and the temperature gradient are not changing between iterations anymore, so it doesn't actually matter which way we decompose the vector, we will still get the same solution. However, if we now zoom in a bit and look at the behavior of the different schemes, we can see that the three approaches give slightly different stability characteristics. And the right angle approach gives some quite large oscillations, the rotation approach gives some smaller oscillations, and the over-relaxed approach is more smooth. And so in terms of stability, what we see here is that actually the over-relaxed approach, the final approach, gives the smoothest convergence. So far, the over-relaxed approach is looking like the most preferred solution for the CFD codes. Obviously, in this example, in terms of accuracy, it wouldn't actually matter which solution we decided to take. But now, if we increase the angle or increase the skewness in the mesh, we can see some slightly different behavior. And in Professor Jasak's thesis, you can skip through to page 142, and you'll also see these results there. And at an angle of 45 degrees, what we see is that actually the right angle approach, that first one, tends to diverge. And as we increase the angle, the rotation approach then also diverges. And what we find is that actually the over-relaxed approach is still able to achieve convergence even at higher angles. So when the mesh is really badly skewed at 60 degrees, we see that the over-relaxed approach is still able to obtain a solution. So in terms of stability at this stage, it would appear that the over-relaxed approach is the most preferable of the vector decomposition approaches. Now, if we just think back again to the equations, again, this is conservation of energy. Remember that the sum of the heat fluxes out of all the faces must be equal to 0. Now, if we have a really bad mesh, so for the last set of results, we looked at theta of 60 degrees, but if theta gets even larger, perhaps to 70 degrees or even higher, then this explicit term on the right-hand side, the non-orthogonal corrector, will eventually lead to divergence and can lead to unboundedness in the solution. And so this presents a problem for CFD codes because quite often that angle theta is larger than 60 degrees, and particularly if you've carried out any CFD simulations yourself with bad meshes, you'll know that we need to find a way of being able to obtain a solution even with these really bad meshes. And the trick that CFD codes use is remembering that this non-orthogonal corrector is treated as a source term. And so because it's a source term, we have a different value in every cell in the mesh. And the trick is, when we have a few really bad cells in our CFD solution, in our mesh, perhaps we have some faces which are at an angle of 70 degrees rather than 50 or 40, then that source term, we can either limit it or discard it and get rid of it completely in those bad cells only. So perhaps in our 5 million cell mesh, we may have 10 or 20 cells where we choose to limit or discard the source term because the cells are really bad. And of course, when we do that, that's going to lead to an error. The solution is not going to be accurate in those bad cells. However, this is a sacrifice because it will hopefully allow us to get a converged solution for the entire domain. So what CFD codes do is sacrifice the accuracy of the solution locally in a few of the really bad cells where the non-orthogonality is high, so that we can still obtain a solution throughout the entire mesh. Because if the CFD code diverges, then we get no solution at all, and that's not very good for the user. And thinking back to what we did before, because in the over-relaxed approach, that vector n2 is going to grow as theta increases, what we find is that actually when we limit or discard this non-orthogonal correction, then actually we get the largest error of the three meshes. And clearly this is a compromise, because the priority with CFD codes is always going to be to get a solution rather than the most accurate solution. So we just accept that if we have some bad cells in the mesh, the solution is going to be locally incorrect, but we will be able to get a solution throughout the rest of the domain. So that just about brings me to the end of the talk. Just to summarize the key points that I've gone through here, an explicit non-orthogonal correction is required because the face unit normal vector, NF, always points directly out of the cell, and this is not necessarily parallel with the vector that runs between the two centroids across that face. And if we have a perfectly square or rectangular mesh, those vectors will be parallel, but the general case is those vectors aren't parallel, and so we have to account for that in order to evaluate the dot product. The way we do evaluate the dot product is we decompose NF into two vector components, N1 and N2. N1 is going to be parallel with the vector between centroids, and N2 is just going to be the residual of whatever is left over in that decomposition. And there are a number of methods we can choose to perform this decomposition. I've been through 3 in this talk, and the choice of method will affect the stability of the scheme and the number of non-orthogonal corrector loops that we need before we get convergence. Of course, regardless of the method that we do choose, if we carry out enough non-orthogonal corrector loops, we will obtain the same solution. So we will get the same accuracy. And several authors in the literature have investigated these schemes, and it's been found that the over-relaxed approach gives the smoothest convergence and the best stability on highly skewed meshes. So the over-relaxed approach tends to be the approach that's adopted by the majority of CFD codes. So that brings me to the end of the video. I hope you guys found it useful and interesting. Let me know what you guys thought. Drop me a comment in the comment section below. I really do enjoy reading and responding to your comments, and I try and respond to them as quickly as I can get around to. And just before wrapping up, once again, I'd just like to thank all of you for continuing to support the channel and watch my videos. It really does mean a lot to me. So thanks a lot for your support, and I'll see you next time.